So you are always, you are already knowing this hydrostatic pressure. When there is no shaking, then also pressure is active, and that pressure is outward, and at the base there is a uniform pressure. Okay, so this is hydrostatic pressure. And you know what is this maximum value here? Gamma W into this height. If it is some other liquid, then the gamma will change. In case of water, you will use the corresponding unit weight. The expression will remain same. What happens in dynamic condition? Two types of pressures are there. Okay, this is the impulsive. Impulsive component of hydrodynamic pressure, and it will be acting outward. That means it will be pressure on one wall and it will be suction on the other. Okay. The fluid will try to move in the direction opposite to the acceleration, or rather it will try to remain in its position. Okay, and as a result it will apply pressure on the opposite wall and suction on the other. Okay, so look at the direction carefully. Here on both the walls in static condition it is applied outward. Here on one wall it is outward and the other wall it is inward, and accordingly on base also it will be like this. So here it will be downward on half of the base, and half of the base it will be suction. That means upward it will be. And if you consider resultant of the force, okay, it will at certain height. That height we represent as H. Yes. Hydrodynamic pressure, when the tank is moving, let me say, towards right, water will try to move towards left. As a result, it will apply pressure on this and suction on this. And also when the pressure will be applied here and suction here, because the pressure at any point has to be in equilibrium. Okay, so if it is suction here, at the base it will act upward, whereas here on the base it will act downward. Okay, this is under horizontal action. Okay, so when we have applied horizontal acceleration here, there is no net force acting in the vertical direction. So half has to be downward and half has to be upward. Suppose the acceleration was in vertical direction. So it has a vertical acceleration as well. So what will happen in vertical direction? If the tank is going upward, vertical direction, what do you think? Can the water vibrate now? how it will vibrate? It will vibrate as an incompressible material. Okay, and it will vibrate up and down, and due to that there will be uniform pressure here. Okay, either in this direction or when the earthquake reverses, this direction will reverse. What will happen to the walls? Will there be any pressure on walls also? Is it possible in a fluid that you apply pressure in one direction and not in the other direction? How the equilibrium will be satisfied? So pressure is uniform on all the directions. So if it is acting on the base, it will be acting on walls also. In the same manner as the hydrostatic pressure. Only thing is that this pressure will be now, earlier I have written as gamma WL, so actually it was rho into G into H. How much it will be here? In this case, you can guess. Rho into AB, the acceleration in the vertical direction, into H. So in place of G, what is G? G is also acceleration due to gravity in vertical direction. So that acceleration due to gravity either increases or decreases by AB. So the role of AB is what? It is simply increasing the acceleration in the vertical direction. Okay. Or reducing, depending on in which direction the earthquake motion is coming. So this will be due to the vertical movement or vertical component of earthquake. So it will be either increase or decrease. Okay. Then this height HI, this is representing the resultant of the horizontal component only. Okay, which is acting on the walls, but due to this pressure acting at the base, which is downward on left side and upward on the right side, due to that what will happen if we consider base pressure also, the effect of base pressure, this will cause overturning. So if I have to calculate bending moment on the walls, I need the pressure acting on the walls. This will not cause, the base pressure will not cause any bending moment on the wall, but when you consider the overturning of the tank as a whole, then this pressure acting at the base will also cause an overturning component. So if you consider that also, then this height of the resultant will increase, and this will be represented by HI star. So HI is representing the height of the resultant pressure acting on the walls, and HI star is representing the height of the resultant pressure on walls as well as base. Expressions for HI and HI star I will give you, and it is available in the code also, and let us see. So you have the code copy with you. Look at figure 2. Let me complete the conductive part also, then you will be able to understand the whole figure. As I told you that the convective motion is occurring in the top portion of the water. So at the top, that pressure will be more and it will reduce as it will as the depth increases. Okay. This also will have pressure on one wall and suction. Sorry. On the other one. And at the base also, pressure here and suction. This height this will be taken by h. And if I consider the base pressure also, then this is x6. Now look at this figure. It gives you hi by h and hc star by h. H is the depth of water in the water. Hi and hc you see here. And it depends on h by l. What is h by l? H is this and L is this. So in case of a shallow water tank, like yesterday I have given you two examples. In one case it was very shallow. So when it is shallow, what will happen to Hi? Consider two cases. One is this and another is this. In the first case, what do you think? Hi will be higher or Hc will be higher? And in the second case, Hi will be higher or Hc will be higher? What do you think? So look at the figure. Hi by h okay, that remains more or less constant, about 40%. Can you see that? The form line, the lowermost form line. Whereas Hc by h is more, always more than Hi. For all values of h by l, it is more. And as h by l is increasing, it is increasing. Now look at Hc star and Hi star. At lower values of h by l, that means shallow water tank, these are the values are greater than 1. What does that mean? Can Hc star or Hi star be more than the height of the water tank itself? But the whole graph shows like that. Yes? And it more than? Due to sloshing. Due to sloshing what it will do? Now how can I apply pressure? If the sloshing wave height is more than the height of the water will spill out. How it can be more? it can be more because of the pressure acting at the base. This moment, overturning moment. Okay, this is also included in HC star and HI star. That's why HC star and HI star can be more than H. So when the water tank is very shallow, it increases, okay, and it can be even more than 2. Okay? Yes.
Convective mass, why it would be raised towards the
Sorry, convective mass?
higher separation?
Because we discussed that the sloshing motion occurs in the top portion. Here, if you see, only the top portion there will be sloshing occurring. In the bottom portion, what will happen? Due to the weight of the water at the top, the pressure at the top, it will be rigidly attached to the tank and it will move along with the tank. So the bottom portion will be participating in impulsive motion. The top portion will be participating in convective motion. So naturally the convective pressure at the top will be more. Impulsive pressure at the bottom will be.
Sir,
Yes.
in that case, why this stress distribution is changed at the
Sorry,
top?
what the?
Pressure distribution. So at the last diagram.
You mean here or here?
This one.
Huh.
At top there is maximum pressure.
That's what he was asking. That's what I was trying to answer. That when the water is moving, the top portion is sloshed. Okay. Bottom portion is not sloshed. Bottom portion is moving rigidly. So this relative motion is more in the top portion and it becomes less and less in the bottom portion of the water. With the depth, this portion goes on decreasing. Okay. So that's why the bottom portion, the impulsive component is more. In the top portion, the convective component is more. Yes. Related to some of this. So you can think that it will be something, it will not be equal, but it will be something like when you are doing, the pressure will be equal. But there is one more problem. This pressure and this pressure are in different phases because it is a dynamic motion. The impulsive component is changing with the period of vibration of the tank itself, whereas convective will have its own period. So it's not necessary that when this is maximum, this will also be maximum. So this is variation of the peak pressure with depth. But this itself will change with time. During earthquake, this is also not constant. The water will be vibrating with its own period. What is that period? That also we will discuss. So it will be vibrating with its own period, and the period of vibration of this is much longer than this. So by the time the tank will have several cycles, the water will complete one cycle. Okay? Now, how to calculate these pressures? So for that, we use what we call 2 mass model. So this we will represent the effect of water, we will represent by 2 masses, Mi and Mc. Mi is connected rigidly, so this is the rigid link. Okay, and this stiffness is Kc. this height at which this mass is attached is Hi, and this height at which the convective mass is attached is Hc. Again, how to get Mi and Mc? You can see this figure 1, or rather in figure 2 itself, figure 2a is giving you that. And sorry, this will be Kc by 2 and Kc by 2. Total stiffness is Kc, and I have shown 2 springs. So each spring will have half that stiffness. So please look at this figure 2a. It shows you the variation of Mi and Mc with h by d or h by l. One figure is for circular tank, figure 2 and figure 3 is for rectangular tank. Variation is similar, values may be different. So for h by d, you can calculate Mc by m and Mi by m. Sum of Mc and Mi will be equal to m. So as h by d is increasing, what is happening to Mc? Or what is happening to Mi? In case of a deep tank like this, almost 80% of the mass will act in impulsive mode, and about 20% of the top that will act in convective. Okay. And when it is shallow, almost 80% or 90% mass will be convective. Whole of the mass, almost whole of the mass will be vibrating in convective in case of a very shallow water tank. Okay. So these masses you can read from these graphs. You can calculate Mi by m and Mc by m from these charts. Okay. Then you also need Kc. So in the same graph, Kc is also given. Okay. So it is given as Kc h over mg. Okay. This is some factor, let us say f. Okay. Given, so Kc, this f is dimensionless factor. So Kc will be mg by h into f. What is the unit of mg? M is mass, g is acceleration. So what is the unit of mg? Newton. And h? Meter. So Kc will be Newton per meter. Factor you will get from this. Look at this value of the factor. What is happening to the stiffness? As the depth of the water tank is increasing, what is happening to this stiffness? Yes, it is increasing. Okay, so what will happen to the vibration of the water, period of vibration of the water here and here? In which case you think that the period of vibration will be longer? In case of shallow tank, it will vibrate slowly. Here, impulsive component will be more, and at the same time, the convective component, convective vibrations will also be occurring at higher frequency. Okay, rapidly, those vibrations will be occurring. So you can visualize the behavior. Now, we need to calculate the period of vibration of this. So let's first take ground supported tank. The tank is kept on the ground. In impulsive mode, the water is attached to this. Okay, so this is our M, and this height is H. Suppose it is a rectangular plan is like that. So on this wall, it is acting like this. On this wall, it is acting like this. So how can you calculate period of vibration of this? This wall under this pressure and its own inertia force, this wall will start vibrating. Okay, so this wall will vibrate, this wall will vibrate under this MI and its own inertia force. Let us say the mass of the wall is MW. So what we will do, we will take a strip here. This strip will act like a cantilever. Let us assume it has its own mass and it also has the mass attached to this, which is M. And it is pressure here, suction here. So it will be applied to both the walls. So which is acting on one wall is Mi by 2. Agree? So the code says that you can treat it as a uniformly distributed load Q. Actually, due to Mi, also there is a distributed pressure. That distribution is not uniform, we have seen. Okay, the pressure due to Mi is not uniform. It was 0 at the top and it was increasing. We are assuming it to be uniform and MW also. Okay, so we will assume a uniform pressure, and this uniform pressure Q we can get as Mi by 2 plus MW into G, and we have considered a unit strip here. So the width of the strip, this is the total force, okay, into H. We have divided by the area. So that comes out to be the pressure or UDL acting over unit strip width. Units will be Newton per meter square. Under this, this is going to deflect like this. Do you know how to calculate period of vibration of this? Yes or no? A cantilever, okay, having this much mass attached to this, can you calculate its period? How?
We will calculate deflection at the end.
Deflection at the end, here. Okay, then
Both sides.
it is a continuous system. Okay, it is distributed. So you have done in theory of vibration how to calculate the period of vibration of a cantilever. You can do that. So its period of vibration will be calculated as a continuous system. Okay, but code says that you can simplify it. You can assume that whole of the mass is acting at an equivalent height h bar, and this h bar we can calculate as from the resultant of these two masses. So that will be mw into h by 2 plus mi by 2 into hi over mw plus mi by 2. This is the resultant height.
So the height of cantilever will be height of the wall divided by half of the wall.
What?
Height of this cantilever you have considered.
Height of the cantilever is h. This is h. That is the height of the tank. But where the force will be acting, resultant force will be acting, that will be at the center or resultant of its own inertia plus mi, which is acting at hi. So mi into alpha h, that will act at the height of hi, and its own inertia force will be attacked. If we assume uniform acceleration, then it will be at the center of the ball. This is approximation. Okay. We have considered pressure on the wall, and the pressure on the wall is occurring due to mi into the axis. Why? The pressure on the base will affect the vibration of this wall. It will change hi star. So it will participate in overturning, but it will not participate in the vibration of the wall. In vibration of the wall, it will be only the pressure acting on the wall. That's why we have given two heights, hi and hi star. So when you are considering overturning of the tank as a whole, then you will consider hi star. When you are considering pressure on the wall or period of vibration of the wall, then it will be hi. Okay.
So which is the height up to which the water is filled in the tank? B is the width of the tank.
B is the width.
But
Okay.
sir, impulsive force is acting up to the action height only.
Acting over the whole height. You see, pressure is acting actually over the whole height. Resultant is acting at, you see here, it is acting over the whole height, but it is not uniform. So resultant is acting at hi. So here we are representing it by its resultant. Actually it is acting over the whole wall. That's why this Q, the real problem is this. The actual problem is this, where the pressure is acting over the whole height. That was the actual problem. We have simplified that like this, because this can be solved easily. Then what we will do, we will calculate the displacement here, delta, and you know the formula. If you calculate displacement due to the mass, then T is 2 pi square root delta by G. And how much is the delta? the total force okay into h bar q by 3m. So that will be total force is q into, we have calculated per meter square, so q into h into over 3e. E is the material of the wall, whether it is a steel tank or concrete tank, that will decide. And I is, B is unity, PQ by 12.
Sir,
Yes.
delta you are considering will be at the location of that result vector and the RA.
Location of the result.
Why?
That's the formula is. So you apply the load. Suppose you have a cantilever. Cantilever may be anything. It is massless. Mass is added here. Mass is applied here. You have to calculate its period of vibration. How do you calculate? Let us say this mass is m. So what you will do? You will calculate this displacement delta. Omega is actually the square root of k by m. Okay. In terms of this delta, what is k?
You will have to calculate.
अरे यार कैलकुलेट करके कर ऐसा क्या बात है? k in terms of delta, mg by delta. Is equal to square root of mg by delta by m. M will cancel out. So omega is square root of g by delta. So what is t? 2 pi by omega. So that is 2 pi square root delta y. That's what we have used here. This delta. So this is m in our case is mi by 2 plus mw, and this distance is h bar. So how much will be delta? And this m is also equal to, how we have obtained q? Q we have obtained as mi by 2 plus mw divided by bh. So this is also q. So q into h, okay, into l, that is h bar over 3 unit width. Q is calculated on unit width only. Now we have divided it by b by h. B into h, sorry. So we have divided it by bh over the whole wall area. So total mass we have divided by the whole wall area. So it becomes per meter square, sorry. And unit width, so per meter square is same as per meter. Now this is for rectangular tank. What will happen in a circular tank? I have shown you that this pressure varies like this. What will happen here? Will the pressure be uniform? what will happen to it? My drawing is so bad. What do you think? Will it be hoop stress? Oh, sorry, hoop tension? Will it occur? How it will vary here? Can you guess? It doesn't need any analysis. It's just visualization. On one side, it is suction. On one side, it is pressure. In case of rectangular water tank, it was easy. On one side, suction, one side, pressure, and it was uniform over the whole wall. What will happen here? Will it be uniform? No. It will be pressure here in this portion, half of the tank, it will be pressure, and half of the tank, it will be suction. And because it is circular, so it cannot be constant. It will be maximum here and here, and it will reduce towards center. So this is how it will be acting on a circular water. Otherwise, how this type of variation is possible? There is no other possibility. It has to be suction here, pressure here. So how else it can vary? It has to gradually change. It has to change from pressure to suction. How it will change? It will gradually reduce and then it will go in the other direction. So the period of vibration, naturally here we cannot calculate using unit strip method, which we have done in case of rectangular tank. Okay. So here either you perform a finite element analysis with this, or empirical expressions are given in code. The Ti is CIH, the square root of rho divided by square root of T by D, okay, square root E. Rho is the density of liquid, T is the thickness of the wall, D is the diameter, E is the modulus of elasticity of the material of the tank, whether it is concrete tank or steel. So you can see that rho is representing mass. So it is square root of m in some way, and T, E, these are representing stiffness. So it is also something square root m by k. Okay, and this coefficient Ci is given in the code. Figure 5, you look, coefficient Ci is given. Okay?
So,
Yes.
how to decide that when we have to go for finite element analysis or not? Here we are saying that to get in time, so we have to.
So in the code, the expressions are given for simple shapes of water tanks. Only two types of water tanks, those are rectangular and circular. If your tank is of any other shape, like I have shown that conical. Hints still you can consider as circular. So base width is not there, but still to some extent you can apply. But if it is conical, like that or any other shape, you will find water tanks are in very fancy shapes, so not only these. In that case, you do not have any other option except doing a finite element analysis. Okay. And when you are doing finite element analysis, it is not only the finite element of the water tank, you have to do finite element modeling of water also. Okay. And finite element modeling of water cannot be done in the same way as that of a structural element. We need different elements. Okay. In software language, they call that acoustic element. So those elements will be needed to simulate water. Okay. Some of you may work on dam water interaction. There is dam, behind that there is reservoir. In the reservoir there is water. And if you have to analyze that, then the water also you have to model using finite element, and those finite elements are different. Finite element formulation is different than what we teach you in class A. Those are structure. The finite element application to structure. For fluid, it will be different. But software are available in which those acoustic elements are available. You can learn those and you can do fine. So if water tank is of a irregular shape, not rectangular or circular, then you have to go for fine. Okay. So this is about TI. TC, the convecting mode, it is very easy. Omega is the square root Kc by MC. So TC will be 2 pi the square root MC by Kc. That's Kc also you know, MC also you know. You can calculate. An alternative method also given in board. In case of circular water tank, you can get TC as CC square root D by O. And rectangular water tank, TC is CC square root L by O. Okay, L is the dimension of the water tank in the direction of shape, and B is the direction of the water tank perpendicular to the shape. So if you are considering shaping in this direction, this is L and this is B. In case of circular water tank, everything is B. Both are B, so there is no point. Okay. Now this CC again is given for circular water tank. It is given in figure 5, and for rectangular water tank it is given in figure 7. Okay. Figure 2, A and B. That's what I explained here. In case of a shallow water tank, almost whole of the mass is sloshing. Whereas in case of a deep water tank, almost all of the mass is impulsive, is moving with you. So here 80% is impulsive, here 90% is convective. Figure? Sorry, which figure? Figure 5. Figure 5. Huh. What are you saying? Convective coefficient is less than impulsive coefficient, yes. Because I told you, when water is vibrating with respect to the water tank, the period is longer. And when the water tank is vibrating with the tank, okay, its period is smaller. In sloshing mode, the water is having longer period.
Yesterday you said that yesterday you said that initially water is not vibrating, like with the
Yeah, that is static.
that is static, and that is due to the damping of the water. You said
Damping of the water? No, it has nothing to do with damping of the water. The frequency of vibration of the water, okay, is less. Period is long. I told you the sloshing. What you see, impulsive you don't see. When the water is moving with the water tank, you can't see it. Okay. What you will see the sloshing part, the convective part. And in convective part, the frequency of vibration is low or the period is longer. So in the later part of the earthquake, the waves have longer period. Although intensity reduces, but the period increases. And that period is matching with the sloshing period of the structure of the water, convective period of the water. And that's why later part the convective motion is started. And then you see that the water is vibrating. But actually the water has started vibrating earlier also. Earlier it was vibrating mostly in convective. Sorry, impulsive. Okay. So last thing for today, how to get the period of vibration of overhead water. So in case of overhead water tanks, again two mass model we will make. MI and MC. MI is connected rigidly, MC is connected through these springs, KC by 2 and KC by 2. This is it. Okay. This is, let us say, height of staging, HF. This is HI and this is H. So you can represent like this. This is the stiffness of staging, Ks. This is the mass of the water tank structure. I am calling that also MS. So MS is mass of the water tank. Okay, and MI. And at what height it will act? It will act roughly at HS plus H. Actually, we should calculate CG. Okay, where the water tank CG is there, where this MI is there, roughly you can take it HI plus H. Okay, then the period of vibration TI is 2 pi square root Ks Ks over mi plus m. Now other way around. I am writing period, which is going to be mi plus ms divided by and dc will be 2 pi square root Now you can visualize the next step. Once you know the period, what is the next step? You will calculate AH, multiply AH by the masses, you will get the force. Okay. You should know at what height these forces are acting. Okay. You will get the bending moment and shear force in your work. That we will take up when we need to know action. In the meantime, to go through this code, you have decided